Okay, so today we will begin with we will continue with the ordinary differential equations theory part and introduce a few new algorithms. Now you might wonder as to why we would want to bother about new algorithms at all. After all, as I said in the last class, the Runge-Kutta fourth order is pretty decent. However, as is often the case, especially in numerical algorithms, there is really no one algorithm which works the best for all possible situations. Okay, and depending on what you really want out of your algorithm, you would perhaps want to look at several possibilities. Now, we cannot simply look at all possibilities. There's way too many things to look at. Okay, so just hold on a bit. So once again, this is an old slide, and the real problem is that I've not really had much of a chance to revisit this slide this morning. I had too many other things to do. So I might even have forgotten some of the stuff that is on the slide. Hopefully, that will not be too much of a problem. Let's see what we are talking about. As I said, there are many reasons why different algorithms may be needed. And there are many situations when no matter what algorithm you use, you will run into some kind of trouble or the other. And one of the very important notions at work here is what is called stiffness. That is stiffness of a seem to be having some kind of trouble here. Anyway. So the stiffness is one issue which is often going to be of trouble, going to cause trouble to us. The basic idea behind stiffness is simply this. There are many ODEs in which small changes in the initial condition or in the coefficients in the numbers may lead to a very large change in the output. And of course, whenever you're using numerical algorithms, remember that there can be small changes even when you don't want to cause changes. You may have small changes because of, say, round off errors. So you will have to be especially careful when you are dealing with stiff problems. And for those, the kind of algorithms we have been talking about are really not very good. Let me just show you why. I'm going to show you an explicit case where the kind of algorithms we have been talking about, which are called forward algorithms, that is, given your y now, you try to find out y later using the slopes that you get either at the beginning of the interval or somewhere in the middle of the interval, etc., etc. But of course, the more complicated the algorithm is, the more difficult would an explicit calculation showing why it is going to be problematic for a stiff problem is going to be. So what we are going to do is we are going to analyze what happens for the simplest thing of them all, that is the Euler algorithm. Now, you should take you a bit of thought to convince yourselves that the same problem will plague the other methods as well, the methods we have been talking about so far. So let us see an example of that. And first, what exactly is this? This occurs mostly when ODEs have rapidly varying solutions. So small changes in the time, small changes in the initial condition can cause huge problems. And now, if it really had just a rapidly varying solution, one very easy way to handle that would be to use a much smaller time interval. Right? Because then if you use a small time interval, then the solution will not get much of a chance to vary. So you will be able to take a look at this very much more accurately. This is exactly what the adaptive methods really work at. However, if you have two different kinds of time scales, you have both rapidly varying and slowly varying terms, then just using a very, very small time scale to capture the rapidly varying terms more accurately actually is a problematic thing, especially if the time scale changes as the thing progresses. Then what happens is you're left with very, very small time intervals, and that may not be very good for you, especially because you may have accumulated huge amount of round of errors. So just an explicit calculation for this. So we are going to consider an initial value problem, which is a very, very simple one. Dy dt equals minus 15y with y0 equals 1. So can anybody tell me what the solution to this equation is? This is an equation you should be able to solve in your head. You don't really need to do any detailed calculation for this. So, just to prove that I'm still connected to you, can you give me the solution to this one?
e to the power minus 15t.
E to the power minus 15t. Right. That's exactly what the solution is. So this is a very simple equation to solve, and of course nobody would really solve this using numerical methods. But I want to show you what would happen if you try to solve it using numerical methods. Like in this case, if you are using Euler. Of course, the real solution dies rapidly down to zero, as it should. That's obvious. But let's see whether Euler actually tells you that. And what we are going to do, oops, I messed this up. So I'm not very sure where the am came from. Actually, the Euler solution to this is yi plus 1. I also messed it up rather badly. Yi plus 1 is yi plus yi dot h. Right? That's what the Euler solution is. Right? The approximation of y in the next time step is the value of y now plus the derivative at the beginning of the interval yi dot times h. So there should be a plus in between yi and yi dot h here. It's not a product. Which of course, because yi dot h in this case is simply minus 15 yi h, you get yi into 1 minus 15h. So here, you don't really have to calculate these things, calculate the solution numerically. You can even figure out what is going to happen if you were to use the Euler solution, depending on what this factor is. It's easy to see that what you are doing is multiplying the current yi by 1 minus 15h. So the successive y's, they will form what? Okay, what will the successive y's form? y1, y2, y3, y4, etc. Come on. If you get the next y by multiplying the previous y by 1 minus 15h, what are the successive y's going to form?
1 minus 15h whole to the power n.
Yeah. So basically it's going to form a GP, right? Geometric progression. And will this geometric progression die down to zero? Which the actual solution does?
No.
No. Why do you say no? Can you explain that? A geometric progression with a common ratio which is smaller than 1 definitely dies down to 0, right? Doesn't it? So if you're saying no, there should be some reason behind that. So can you just explain that?
Depends on the value of step size.
How?
If 1 minus 15h is less than 0, then we will get some other solution. I mean, it will not behave like that.
Okay, actually, you're almost correct. You're actually correct, but there are some categories here. If h is bigger than 2 by 15, if you take a step size which is more than 2 by 15, then 1 minus 15h turns out to be less than minus 1. Okay, that means it's actually more than 1 in magnitude. What this means is that the geometric progression of the y's will actually end up diverging. Okay, it will be oscillated. It will keep on changing sign from positive to negative, from positive to negative, and so on. But in the long run, it's going to end up diverging. So that's, of course, completely opposite the behavior which the solution to this differential equation should have. Is that okay? Now, so this Euler solution actually oscillates unboundedly. It does oscillate because of the fact that you have a negative common ratio. So it goes from positive to negative and positive to negative and so on, but it keeps on doing that unboundedly. Now, if h is somewhere between 2 by 15 and 1 by 15, 1 by 15 simply because you have 15 here. Okay. Then what happens is this 1 minus 15h factor, the common ratio, is negative. It's smaller than 1 in magnitude. So it will die down to 0 in the long run, but it will die down to 0 by oscillating between positive and negative values, which, by the way, the actual solution never does, right? The actual solution monotonically decreases from 1 at its initial point to 0 for large t, and does so rather rapidly. But this solution, the Euler algorithm, actually shows you oscillations. Okay, which is of course not really there in your problem. Now you should notice that when you are doing a numerical solution, of course you don't expect to get exactly what an analytical result would have given you, but you expect the qualitative features to stay the same. Here what is happening is, when h is bigger than 2 by 15, of course it's not even qualitatively, well, it's not even, forget qualitatively, it's nowhere close to the actual answer. It actually keeps on growing instead of decreasing. In this range, 2 by 15 to 1 by 15, in between that, it gives you a decrease to 0, but it gives you a qualitatively wrong behavior. It gives you oscillations. So forget numerical accuracy, even qualitatively is wrong. It's only when h is less than 1 by 15, then this common ratio is less than 1, so it's going to decrease monotonically to 0, the way the actual solution does. Now you might say 1 by 15 is anyway too large a value of h. We will just use a smaller value. Now that, remember, is simply because you have used a 15y here. Suppose this had been 15,000y. Then for the same thing to work, h would have to be less than 1 by 15,000, a very, very small value of h. More importantly, this is one thing you have to realize, that very often, if you just use a numerical algorithm without analyzing what it's going to do, it might end up giving you a solution which is completely crazy. And that's not so dangerous when you actually know the exact solution, because then the crazy solution can be easily understood to be crazy. But if you're doing the solution to an unknown problem, you should definitely still use all the tools that are available to you to try to understand the solution as much as possible before you trust your numerical calculation, because your numerical calculation might very well show this kind of behavior. And it's not as if this behavior is erratic or impossible to understand. It's just that you have to analyze the thing properly first. So just to look at the behavior, this is this orange curve. I hope you can see the curve. The orange curve is the exact solution. The cyan dots here, the cyan line joining the dots, these are the results when h is smaller than 1 by 15. The green one is when h is between 1 by 15 and 2 by 15. So you do get a decrease, but the decrease is rather slow and is rapidly oscillatory. And the purple one, of course, is the worst of them all, where h is more than 2 by 15. it simply keeps on blowing up. In fact, it blows up so rapidly here that after 2 points, I can't even draw this on the same scale. Okay. So this is a word of warning, and it's important to understand that just blindly using numerical algorithms can lead you into all kinds of trouble. So it's not enough just to understand the algorithm. It's also important to understand the limitations of the algorithm. However, let me show you that there's a very easy way of getting out of this particular problem. But before that, are there any questions about this? Okay. So I'm assuming that I'm still audible and there are no questions, right? Fazal, saying yes sir on the chat hardly helps because I have to come out of the presentation to see your chat, unfortunately. So if you want to say something, just unmute and say so. That is while I'm presenting. Okay. Anyway, thanks for that. So let's try to see how you could solve this issue. This issue meaning simply the issue of qualitatively bad behavior. The Euler method is not great as far as numerical accuracy is concerned. It's not meant to be. Okay, could you just hold on a bit? I have. Okay, unfortunately, there's going to be quite a lot of noise now. Anyway, can't be helped. So, what I'm going to discuss now is what is called an implicit Euler method, and this is essentially a way to handle the stiffness problem. You have to realize that it's an Euler algorithm, so it's still not going to be very, very precise, but it's at least going to be qualitatively okay. And that is the basic idea. Of course, if you want more accuracy, you will try to do an implicit version of something, some other, say, more complicated algorithm. Say, you could do implicit versions of the Runge-Kutta fourth order and so on. So how you do this is, instead of taking the derivative at the beginning, take that at the end. Okay. However, you might very wonder that we have already done that, right? We've already done something like the modified Euler method, where we took the derivative at the end of the interval to be the derivative throughout. However, this is different. So let me just tell you what this is, and then I will ask you to point out what is different here than the modified Euler or the endpoint Euler method. Okay, so there are some stray things which have got in. I don't know how. This means the SP09 is, you can simply ignore that. Okay, what this means is yi plus 1 is of course yi plus y dot I plus 1h. Okay. Now, in the modified Euler method, what we did was estimate yi plus 1 by using the value of y at the very beginning of the interval, then moving it forward using the slope at the beginning till you reach the end. But here we are doing nothing of that kind. We are just taking the expression for y dot I plus 1. Remember, our y dot is minus 15y. So I just put that in. I get yi minus 15yi plus 1h. Okay. So notice the difference between what I had for the ordinary Euler method, which was yi minus 15yh. Here I have yi minus 15y plus 1h. So can anybody tell me what is the big difference between the two cases? To compare this with the Euler method, the only real difference is here you have yi plus 1 instead of yi. So why is this so different? What is the real difference? Can anybody tell me that?
Sir,
Yeah.
how could I know that? How could I know the value of yi plus 1?
Well, can anybody tell me how you could know the value of yi plus 1? In fact, that's part of the answer to the question that I just raised. But can anybody tell me how you can find out yi plus 1? From this?
For this problem, it is a constant. I mean,
No,
the
yi plus
factor.
1 is not a constant, of
No,
course.
yi plus 1 dot is a constant.
No, it's not. It depends on the value of y, right? And the value of y changes. Remember, it's minus 15y,
okay, yes,
not minus
yes,
15.
yes. Okay, sir.
But a very good question was raised. How do I find out yi plus 1 here? What's the answer to that? Come on.
Hello, sir.
So it's also a GP here.
Huh? What? Sorry, I couldn't hear you.
So it's also a GP in this case with y plus 1 equal.
That's secondary. The important thing is how do you find out yi plus 1? Then we'll see what it. Then whether you're right or wrong that's okay, but that's not really the important point. Tell me how
So we can take that 15yi plus h on the left hand side.
exactly. So what you're doing is you can solve for yi plus 1, right? The difference between the Euler case and this one is in the Euler case, it was a formula for calculating yi plus 1. You had yi minus 15yi which means you already know everything on the right hand side. You just use that as a formula and find out what yi plus 1 is. On the other hand, here you are looking at this as an equation for yi plus 1 h. Yi plus 1, right? Which is, you just move this whole thing to the other side. In this case, the equation is very simple to solve. In other differential equations, this equation may not be very easy to solve. Okay, I've deliberately chosen a very simple differential equation where I can show you the result explicitly. And you're right that once you solve this, this is called an implicit expression for yi plus 1. Not
Hello.
Sir, you are not audible. Sir, you are not.
okay. Am I back or not?
Yes, sir. Yes.
So what did you miss, or what did you hear last, Moribor? How is it possible for you to tell what you missed? But anyway, where was I?
So why is it called the implicit Euler method?
Okay. Is there a question, or was that the one thing
No,
you
that
heard
was
at the end?
yes. That's what I heard at the end.
Okay. So as I said, this is an implicit expression for yi plus 1 because you have to solve this for yi plus 1. It's not a formula which tells you what yi plus 1 is. And in this case, at least, the solution is very easy. Usually, it is not this easy. Okay. Usually, the equation you get for yi plus 1 may not even be possible to solve analytically. So you may have to resort to numerical methods for solving equations to find out yi plus 1 from here. Okay. However, the advantage that you have is this. If you look at this expression, yi plus 1 is yi by 1 plus 15h. This is also a GP, as was pointed out. But what is so great about this GP? Can anybody tell me that? Why is this GP better than the previous GP?
It will always convert, sir.
It will always converge because h is positive. So 1 plus 15h is always more than 1. 1 by 1 plus 15h is always less than 1. It's not only always going to converge, it's going to monotonically converge to 0. Exactly the correct qualitative behavior for the problem. So the problem that we had with Euler method, that is, if h were too big, you would see qualitatively wrong behavior. That will never happen here. Okay. In fact, that is one of the reasons why implicit methods are actually better. That implicit methods essentially ensure stability of your solution. Your solution is always going to work nicely no matter whether your equation is stiff or not. Of course, if you want more, remember there are two different things here. One is qualitatively correct behavior, the other is accuracy. If you choose a huge value of h, this is not going to be very accurate. But if you choose a decent value of h, it's going to be both accurate and stable. And implicit versions of, so notice that in the modified Euler method, we actually use yi plus 1, but there we did not use the actual value of yi plus 1. We estimated yi plus 1 using the value of yi plus h times the slope at the beginning, let's say. So that was still an explicit method where given your values of y at the beginning of the interval, you can calculate every step without having to solve anything. Here on the other hand, you have to solve for yi plus 1 at the end of the day. And as I pointed out, in this case, it was easy to do. In many other cases, it will be horribly difficult to do by hand. But then you can always resort to numerical methods to find out what yi plus 1 is going to be. So implicit methods are often better. Okay. So this is, so the previous solution, the Euler solution was conditionally stable. It was stable only when h was less than 1 by 15. Okay. When h was between 1 by 15 and 2 by 15, it's still unstable. It gave you oscillatory behavior where there is none in the actual solution. And here it is unconditionally stable. You don't have to insist that h is less than 1 by 15 for this to be stable. Okay. Now there are slightly more complicated things that can happen. For example, if you consider this particular ODE, can anybody tell me why would you expect trouble here? This is also an equation which is very easy to solve, but I'm not going to expect you to be able to solve it in your heads just by staring at it. But you should be able to actually. At least tell me what kind of behavior it will have.
So in the large values, then the e to the power t minus t dies out, and another is also depend upon the y's. Then even in the
True. But if you just forget about this term, this would really have given you a linear equation of the same kind as before, right? Except for this additional plus 3000. Okay. So basically what this would do is that instead of going down to 0, it will go to some steady value perhaps. This term inside the value. But steady value is easy to see. The steady value will be in the long run. The steady value will be at y equal to 3, right? When t is very large, when y equals 3, this side vanishes. So the thing will steady out there. But what I am really interested in is that if you look at the solution to this equation, and this is something you can predict even without solving it. If you move this 1000y to the other side to get the familiar form for a linear equation, you should realize that this behavior, the plus 1000y, actually leads to e to the minus 1000t in the solution. In other words, the exact solution here, which you can, okay, exact within 3 decimal places is this expression. Okay. 3 minus 0.998 e to the minus 1000t minus 2.002t e to the minus t. Now, here, for very small times, actually what will happen is this is the term which makes the thing actually vanish, right at t. Without, note that you could always say that this term is so rapidly decreasing that this, you can ignore this, right? E to the minus 1000t, of course, decreases much more rapidly than e to the minus t. Is that okay with everybody? Okay? Yeah? However, e to the minus 1000t is exactly what makes this term vanish at y equal to 0, at t equal to 0. But if you just ignore this, at t equal to 0, you will end up with 0.998. Right? Is that okay? You might think that this term is something that you can ignore because this is going to be much smaller than this. But that's true only for decent times. But for very small time, this is going to be the thing which dominates. Initially, what is going to happen is this is going to cause a rapid, or initially meaning when you're very close to t equal to 0 and moving towards t equal to 0, this is what is going to cause a rapid decrease to 0. And then when t is large enough, this term is going to show up and take all the dominate the behavior. So this initial transient of e to the minus 1000 t will simply die down very rapidly, and then you have this slow exponential behavior which will ultimately cause it to steady out at 3. Now, the point here is that here you have two entirely different time scales at work. One for this very rapid exponential, the other for this much slower exponential. So unless you carefully handle the time step, you are going to get into trouble. So I will not work this out or show you the results here. You should be able to figure it out yourself. The explicit Euler algorithm would simply be this, right? You just take the value of the slope at the beginning at the ith time interval, which is minus 1000 yi plus 3000 minus 2000 to the minus ti, multiply that by h, add that to yi. That is going to give you yi plus 1. The implicit Euler algorithm, on the other hand, does the same thing, except that it tries to find out the slope at the end of the interval, not by estimating what y is there, but by simply using the value of y there. And then, of course, this is an equation you have to solve for yi plus 1. So what I would urge you to do is try to use both the methods and try to see what difference in behavior that will happen for the two cases, depending on the value of your step size. You should be able to analyze and figure it out on your own, by the way. The point is, if you really want to see the very small rapid behavior, that's when you use a very tiny h. If you don't, you're going to miss the behavior anyway. So this is an example of where both the explicit or the implicit Euler algorithm may give you trouble, at least in getting the initial thing right, if you actually don't think about the time scales involved. So once again, my point here is that you have to actually understand the nature of the problem before you actually go and just attack it by some standard algorithm. Okay. So I will next talk about some. Okay, are there any questions here? Because I want to move on to a new kind of algorithm. Okay, just give me a couple of minutes. I will be back soon. Okay, so there are no questions at this stage. Okay, I'm assuming no. So as I said, one kind of algorithm would not really work. So you would have to use other kinds of algorithm depending on your situation. Okay, so what we are going to talk about now is the so-called Adams methods. There's not one Adams method, there are several actually. And we will see what that means. But the basic idea behind the Adams method is to solve an initial value problem, just like in all of these. So You have this equation. Now I've just changed the notation a bit. Instead of t, I'm using x. I don't know why. I don't remember why I switched to x. There may be no reason. It's just that the dependent variable can of course also be called x as often as it is. So dy dx is some function of x and y at x0 is y0. That's the initial value problem. I want to solve this, find out y at intervals x1, x2, x3, x4. Okay. Now suppose I want to find out yn, which is the nth x. Of course, in all these algorithms, you have not found out yn just out of the blue, right? You had found out y. You started with y0, then you had found out y1, y2, y3, yn minus 1, and then found yn. So it's natural to think about it this way. In all the algorithms we have seen so far, all the Euler, all the Runge-Kutta methods, and so on, even the implicit ones that we have talked about, in all of them, what we have done is we have just ignored all the previous information, right? y0, y1, y2, y3, we did find out, but we just ignored them. We just used yn minus 1 and found out slopes between yn minus 1, tn minus 1 and tn at different points by various tricks, and then just use that to estimate yn. But we have some information. We know all the past behavior, y0, y1, y2, yn minus 1, and so on. So why can't we use the past behavior as well? Do you understand the point here? So the question is, can we exploit our knowledge of these prior values to derive an accurate estimate for yn? And the answer is yes. And that is exactly what the Adams methods are all about. Okay. So to think about it, it's really rather natural to think about it this way. After all, we have already done the hard work of calculating all these numbers. Why don't we just use them? So basically, there are two kinds of methods here. They're called Adams-Bashford methods or the Adams-Moulton method. Let me just point out what the Adams-Bashford method is. It may look a bit complicated, but it's really not. It really says, remember, f is this function which calculates the derivative at x and y, right? So since you already know all these points, xn minus 1, yn minus 1, xn minus 2, yn minus 2, xn minus 3, yn minus 3, all these are known, right, at this stage when you're calculating yn. So why don't you take those slopes, the slopes at xn minus 1, yn minus 1, xn minus 2, yn minus 2, say k such slopes up to xn minus k, yn minus k, weight them with different factors beta 1, beta 2 up to beta k, average them together and find out a slope and use that as the slope. So is everybody clear about the difference between using this kind of weighted average of the slopes and the kind that we use for RK4, say?
It's not clear, sir. Yes.
Not.
Sorry. Could you just repeat that? Hello?
Hello, sir. Almost not clear, sir.
Okay, I've not gone to the details of the method yet, but the point really was, just think of what we did when we found RK4, for example. Okay, what we did was, we know yn minus 1 and xn minus 1, and we need to find yn and xn. When we use RK4, what we did was, we estimated the slope between yn minus 1 and yn, between tn minus 1 and tn, by finding out slope at 4 different places inside the interval, right? And of course, since I did not know the values of y actually inside the interval, what I had to do was I had to estimate the values of y inside by using previous slopes that you had calculated. That's how why you had this P, Q, R, S, 4 slopes and you average them. Is that okay?
Yes, sir.
But these are all slopes which are being calculated between Tn minus 1 and Tn. Now you might think that that's actually good because that's closer to where you are really trying to find out your answer. So that will be more accurate. However, notice that you have to estimate all the intermediate slopes because you don't know the y values inside, right? On the other hand, you have calculated all the x0, y0. Say you started with x0, y0, then you went to x1, y1. x1 was trivial, it's just x0 plus h. But y1 is what you estimated. Then you found out x2, y2, x3, y3, and so on. Then each stage, as you went along, you actually can also know f of x0, y0, f of x1, y1, and so on. Right?
Yes.
So the question is, all these slopes that you know the function had before you reach this stage, here you're using at least some of those slopes, the last k such slopes. At x, you are at xn minus 1, yn minus 1, so this is the slope at the, which you would have used in the Euler method. Just f of xn minus 1, yn minus 1. Okay? And the previous slope that you had, here notice that you're not calculating any new point. These are points which you already had found when you got here, right? So xn minus 2, yn minus 2 was a slope that was a point that you used before you got to xn minus 1, yn minus 1. So you take the slope there, you take the slope at the point before that. You take k such slopes. So you take slopes at the k previous points that you had visited. Okay?
Also with weighted average, beta 1, beta 2, and beta 3.
Yeah, and we take them with the weighted average. Of course, you don't necessarily give all of the slopes equal weightage. You would like to give perhaps beta 1 a bigger value than beta 2. Let's say. I'm just guessing because beta 1, because xn minus 1, yn minus 1 is closer to the point that I'm really trying to reach. Right? So maybe the last slope should get a bigger weightage and so on. Now, exactly what the weightage will be, I'm going to tell you that. And how to calculate that. That we are going to come to. Okay?
Sir,
Yeah.
sir, what is the motive of doing this kind of stuffs? Because to use this algorithm, I must have to calculate all points. Since I have calculated all points, so I can use RK4 method or anything
I think
else.
you're missing the whole point here. When you're using the RK4 method, what do you have to do? To get a fourth order accuracy, what you need to do, first of all, RK4 is not the be all and end all. There are situations where other algorithms are better. And especially the function is difficult to calculate. Remember in RK4, what you have to do? You have to find out f at each of 4 times in the middle of each interval. Right? Here, on the other hand, you are using 4 f's which had already been calculated previously. So if you have coded carefully, you would have stored those values of f when you got them. You wouldn't have to calculate them again.
Yes, sir.
Especially
That
if f is
means
very
I
difficult
have-
to calculate.
Yeah.
Yeah?
That means when I have to use this algorithm, I must have to calculate the before points x1,
No, but
xn
you have,
minus 2.
no, wait a minute. You already know the points before, right? You did not get to yn just like that, right? You got to yn minus 1 by calculating all the previous points. Aren't you getting that? Suppose the 10th y, you get the 10th y just directly from the 0th y. You didn't, right? You had to calculate the first, second, third, fourth,
Yes, sir.
and
Yes.
then go to 10th. So at this point, you already know all these numbers that are in here are already known. And in fact, if you cleverly code, you would have actually stored the values of the last few f's already when you calculated them. So you wouldn't have to calculate them again.
Okay.
Okay. Now there is a point to what you say. We'll come to that, but that's really rather minor. But we will come to that. Now there was Adams-Bashford. Remember, I've not told you how to find out beta 1, beta 2 yet. But I just told you the basic idea behind the method. And now we come to Adams-Moulton, which is the other kind. It's really very similar, except for one thing. You do a weighted average of the slopes, right? Just like in Adams-Bashford. But you also take in a weightage of the f at the end, at x and y. So Adams-Bashford takes the weights of all the points before, or takes the slopes at all the points that you, not all the points, the last k points that you visited before, and takes a weighted average of that and uses them as for each. This one takes a weighted average of all those k slopes and the slope at x and y. So what is the basic difference between the two methods? If you were to qualify the methods using adjectives, what kind of adjectives would you use? We have just used that a while ago.
It's
So
an implicit technique.
Yeah. Adams-Bashford is an explicit technique. Because here, this is an explicit formula for calculating yn. Adams-Moulton, on the other hand, is an implicit technique. Because yn is appearing on both sides of the equation. You solve this to find yn. Why would you prefer this? Well, if you have problems with stiffness and stability, Adams-Moulton is going to be better than Adams-Bashford. Of course, it comes at a price. Comes at a price of having to solve an equation for yn every time, which, if the function f of x and yn is complicated, you will have to solve numerically. So that's one additional step. But you already know how to solve equations numerically, and we have pretty efficient algorithms for that. So at the cost of having to solve an equation, you get stability. So that's a small price to pay to get a really good answer. Okay. But now let me just point out how to indicate how to find out these weights in the first place. Okay, so how do you find out the coefficients? I'm doing it for the Adams-Moulton. You could do it easily for Adams-Bashford as well. Now, what you can do is rewrite this equation in this form. Yn is actually yxn, right? Yn minus 1 is y at xn minus 1. So I just moved it to the other side. And I moved this entire stuff on this side to the other side, realizing that these f's, what are they? They are just y derivatives. Right? F's are just the derivatives of y, dy dx. At xn minus 1, at xn minus 2, at xn minus k, and so on. So what we simply do is use Taylor series, nothing else. Now this is the calculation which I will want you to do as an exercise. So I will leave it here. I will of course upload this particular file to the Wheeler. I'm not going to show you the details of how you got to this, but it's actually pretty straightforward. All you do is use yxn minus yn xn minus 1, something called the backward Taylor series. That is, the forward Taylor series is actually how you go from yxn to yxn plus 1. Here you are going back. And so the point is you are writing everything here. Y at xn minus 1, y prime at xn minus 1, y prime at xn minus 2 in terms of y at xn, and use Taylor series backwards. And if you do that, it takes a bit of algebra, and it's no point really my working out the algebra in front of you because it's going to be difficult to follow anyway. It's best that you work it out yourself. If you just went and did that, and so basically what you have done is minus h beta 0 y prime xn, that's fine. Minus h beta 1 was y prime at xn minus 1. So you write that as y prime at xn minus h times y double prime at xn plus h square by 2 factorial y triple prime at xn, and so on. And do it for all the terms. I have not written every term here simply because it won't fit here. It's a slightly lengthy calculation, but it's one which is worth at least doing once. So ultimately, when you gather every one of these terms together, notice that these are the y prime xn, y double prime xn, y triple prime xn, y fourth derivative xn, and so on. By the way, this top line, where does this come from? This is simply yxn minus 1. This H beta 0 y prime xn is already available at xn, so you don't do anything about it. H beta 1 y prime xn minus 1, you use Taylor series. Okay. Then you use Taylor series for H beta 2 y prime xn minus 2. Use Taylor series again with 2h as a time step, and so on. Now, if you do all of this, you find that ultimately you can write everything in terms of y prime xn, y double prime xn, y triple prime xn, and so on. All the derivatives of y prime of y evaluated at xn. Okay. So this becomes y prime xn into something, y double prime xn into h square into something else, y triple prime xn into y into h cube into some other quotient C3, and so on. And this is what you have to work out yourself. That is, the coefficients at least up to 4th order are given exactly by this. This is something I'm stating here, I'm not proving for you, but this is the algebra that you can work out yourself. It's just simply a matter of writing down the Taylor series properly for every term and gathering the terms together. But if this is true, then can anybody tell me what beta 0, beta 1, beta 2, beta 3 should be? First of all, how many betas do you have? How many unknowns? Deliberately switch off the presentation because that might be misleading. How many unknowns do you have?
K number of unknowns.
Exactly, k number of unknowns, and k is up to you. K is the order of the Adams-Bashford method, or Adams-Moulton in this case. Okay. Actually, not k, k plus 1, because beta 0, beta 1 up to beta k. Right? In Adams-Moulton is k plus 1, and Adams-Bashford is k. Okay. So, if for example k is 4, then you don't have, then the equations end here. You have 5 equations, and there are 5 unknowns. You should also go up to C5. So basically, if you want order to be correct, that means basically the first 3 derivatives will cancel out from the expression. So notice that what you are really doing is that you are actually solving an equation to some high order of h, just as we did in Article 4. It's just the method of arriving at that is different. If you make the p of these coefficients vanish, then you have got an order p method. Then your calculation will be correct to order p, and p star p plus and each the p plus 1, etc. will be the order of the error. For Adams-Bashford, in fact, you wanted to, yeah.
Sir, how are these equations consistent?
Why should they not be consistent?
Sir, because I have 3 values for beta 1 plus 2, beta 2 plus 3, beta 3 plus 4, beta 4.
Oh. Good. You have spotted a wonderful thing. So, everybody, please pay attention. You have 3 values for this and so on, and this is simply a copy-paste error. Okay, thanks for pointing that out. These values are, of course, not the same. I copied this line, wrote the next one, forgot to change it. Okay. So your work becomes even more. You can't rely on these equations. These equations are wrong, you have to find out the correct equations. Okay.
Hello?
Yeah.
For
Go ahead.
C3, there is beta 2 start from beta 2, no? Beta 2 plus 2 beta 3.
Yeah. So basically, the equations are wrong, and I don't think I have the time to correct them right now. So that will be your homework. Find out the correct expressions. Yeah, you're right. There will be no beta 1 here in C3 and so on. So try figuring out the correct answers. It's pretty straightforward actually. I just messed up because I copy pasted and I forgot to change the coefficients enough. So sorry about that. But What you should realize is ultimately you do get a consistent set of equations. And sorry about the mess. This one is not consistent. Of course, this one is going to tell you that beta 1 plus beta 2 plus 2 beta 2 plus 3 beta 3 plus 4 beta 4 is half. This one apparently tells you that it's 1/6. That of course is wrong. If I did it correctly, you would get a consistent set of equations which you have to solve. And I've just copied the answers out for you, and hopefully I've got it right. So for Adams-Bashford, of course, you don't have to recalculate anything. You just put beta 0 equal to 0. For Adams-Moulton, you solve with beta 0 in it. So for k equal to 2, you can easily show beta 3 and beta 4 would have to be 0. Then these are results. And beta 1 and beta 2 will have to obey this. Of course, for k equal to beta 2, beta 3 and beta 4 equals 0, you don't really have to show. If k is 2, that means you've only taken the 2 previous points, so you've not even taken 3 and 4. All I'm saying is if you wanted to use the same set of equations for k equal to 2 also, you'd have to start by putting beta 3 equal to beta 4 equals 0. And then you will get these 2 equations. Beta 1 plus beta 2 equals 1 and beta 1 plus 2 beta 2 equals half. And this will immediately give you beta 1 and beta 2. For the Adams-Bashford method, the fourth order, you have to make the first 4 coefficients 0. And this is what the weights come out to be. These weights add up to 1, but they're not really proper weights. These are not weighted averages, note. Plus minus signs. Okay. So now, finally, let me quickly tell you, how would you use the Adams methods? They're often used together. The Adams-Bashford and Adams-Moulton are used together. The idea is solving the... Look, the real problem is solving the nth order, solving the equation. Say Adams-Moulton would mean you have to solve an implicit equation for yn, right? That's going to be often very difficult. So what you use is what is called a predictor corrector approach, which is you use the Adams-Bashford to predict yn, and then you use the predicted value of yn in the Adams-Moulton step to correct the yn. So you don't really use Adams-Bashford and Adams-Moulton by solving this equation for yn. You predict yn by using Adams-Bashford, then you correct it using Adams-Moulton. Okay, I will explain this again in detail in the next class because this is going to be too hurried to really give a proper explanation to right now. And the next class we will also see some code examples that should make it clearer. But one question that was asked at the very beginning about this method, I'm sure this is what was really the worry. You do need the previous k values to start. Okay? But how do you start at all? y0, y1, that is, once you've got to y10, you have 10 previous values, y0 to y9. So you can easily do a fourth order thing. But when you are calculating y4, you need y0, y1, y2, y3. How do you get those? You can't use the Adams-Bashford method for doing that because for y0, y1, for y0 I already know at the beginning. But y1, y2, y3 would have required 4 previous values. I don't have 4 previous values for them. So for y1, y2, y3, what you do is use Runge-Kutta, let's say. Okay. So start the first 4 by using Runge-Kutta and then use Adams-Bashford, preferably use the predictor corrector method. Bashford to predict, Moulton to correct. We are going to explain this in some detail with a code example in the next class. That should be easier to follow. Okay?
Yes, sir. Now it's getting mixed up.
Yeah? Go ahead. Couldn't hear you.
Now it's getting mixed up.
Now it's getting?
Show us the codes.
Sorry, I couldn't hear you at all. Now it's getting what? Complicated or difficult to understand, right? Mixed up. Okay, I understand. That's because I rushed through the final bit in an attempt to finish within the hour, which I couldn't manage even then. I will explain this in some detail in the next class by showing you a code example that should be easy enough to follow them, hopefully.
So just confusion about Adams-Bashford and
Yeah.
the previous method.
Yeah, go ahead.
The previous method and these methods be
The
complicated.
previous methods, in each of the previous methods, what you suppose Runge-Kutta, what do you do? To go from y0 to y1, you need to calculate 4 slopes, right? In
Yes.
between. Okay, and you have to estimate 4 points in between inside the 0 to h interval. These 4 values will not be used later, right? You will not store them, you will not save them, you will not keep them in account. They were just estimated so that you can get the slopes right. Okay.
Yes.
In order to go from y0 to y10, you actually calculated 40 different slopes. Okay.
14
right?
difference. Yes.
And only 10 of those points are at 40 different slopes at 40 different points. Only 10 of those are what you are going to actually use. Is that okay?
So from this previously calculated slope, I can calculate further from another point. So that.
Yeah, so that means that you don't have to actually calculate that many. Just do a quick check. If you just use Adams-Bashford, then what would happen? If you suppose that want to find the value of y at 100 points, if you wanted to do Runge-Kutta fourth order, you would need 400 calculations.
Yes.
Here, 100 would have done, except that 100 wouldn't do because for the very first 4, you would need to do 4 calculations each. Because the first 4 you will have to do Runge-Kutta fourth order. Let's say. Okay?
Okay, sir.
But that's only 16. 16 plus 96. Compare it with 400. Do you realize why this is going to be much less work for the computer?
From different order equation, the
it's not different order. This is also fourth order.
Oh, okay.
So this is as accurate as the Runge-Kutta fourth order method. But Runge-Kutta fourth order, you need 400 steps to 400 values of slope calculation. Now, if the slope calculation is easy enough, that's not a problem. But if your equation which gives you the slope is very complicated, which might very well happen very often, you may have to solve a very complicated equation to find the slope. Okay.
Sir, also the weighted I have to remember, na? Sir, beta 1, beta 2, this for
true, but do you have to memorize those things? You don't have to remember. Your computer has to have a code in which those numbers are built in. That's it.
Okay.
Look, you have to understand the code and why it works the way it does, but you really have to remember the coefficients. That's what nobody ever does. You just go to Google. If you want, you just Google and find the answers.
Okay. Okay, sir.
Having to remember a code is never a problem. The problem really is whether the code is too complicated, has too many steps. Remember, more steps means more round of errors, and all those issues are there.
Okay, sir.
Okay. So here you get away with much less calculation at the expense of a more complicated algorithm. And you actually use Adams-Moulton because that actually simplifies. That actually stabilizes the answer. So you use both Adams-Bashford and Moulton in the predictor character approach. We are going to talk about that. The next lecture we are going to talk about this again with an example, and we are going to talk about symplectic algorithms, which are actually very, very useful for other purposes. Say you want a system, you are coding a Hamiltonian system. One thing that you know is that an energy is conserved in the Hamiltonian system. You want it to stay conserved. Okay.
Okay.
Numerical algorithms, of course, will not conserve the energy because there will be errors, they will drift. Symplectic algorithms help you to handle those issues. So we are going to talk about that in the next class on Thursday.
Okay, sir. Okay, sir.
Okay. Okay. Bye for today.
Thank you, sir.